In this video, I'm going to show you how to interpret CoolSim output results. I have here a data center we use often for demonstration. And you'll notice here it has different kinds of racks. These are racks. You can see the airflow indicator by the arrow on top. This red area right here is a cable cutout. In those racks, you can see it's a non-rectangular room. It has an angled wall, raised floor, perimeter cracks, and room return. This is typically called a room return kind of design. Alright, so now in this model I ran under simulation. You will see that I ran a series of runs. In CoolSim you can run up to 4 variations. Here I turned off some cooling units. So for run 0 I have them all on, but for run 1 I turn one off. For run 2 I turn one off, a different one, and in run 3 I turn a different one off. You're also able to change the airflow rates, which I change a little bit in these different runs, and also supply air temperature. So those are 3 variables we allow you to vary using the feature called crack parameter variation, CPV, crack parameter variation, which is one of the most often things you want to do is n+1. You want to see what will happen to that data center if certain units are turned off. Okay? Now, this model has already been run, and the results are sitting here under Reports, lower left-hand corner, Reports. So I've already gone to Run, and I've hit the Status button, and it has downloaded my output reports, and they're sitting in this tab right here. They can also be delivered to you via HTML. But for now, this is where they are. You can see here, the first thing you see is a summary of the various parameters you submitted, because it's important to remember that the 4 runs are listed here, but you have to remember which one what you did to which run. So we make a summary here for you, so you can say, well, okay, on run 1, these are the parameters I assumed, and run 0, and then run 1, run 2, etc. And you can toggle between any of the 3. Now, under each of these tabs is a full set of output, and that's what I'm going to describe to you today, is how to analyze this output. So the output comes in 2 forms. There are 3D files over here, and there is numerical data over here on the right, and the numerical data is going to be active for every object in the room. First, there'll be a general data center description overview of the parameters, and you can just toggle this and take a look. You'll see here that it was run on the coarse mesh, which is the default, the mesh size, the number of cores used, and then data about the room, size of the room, floor area, height. One of the most important things is this one, flow through the units, those cooling units, and flow through the racks. The flow through the units, the cooling units, always has to be greater than the flow through the racks, or the racks will simply recirculate upon themselves. And flow through the tiles here should closely match flow through the crack units, although it won't always, because you can see here I'm flowing 143 through 1000 through the tiles, but 146 is coming through the crack units, and that's because some of it goes to things like PDUs and other places. They'll be close, but they won't always be equivalent. So this is all numerical data. One of the more important areas to look is right here, Data Center Energy Report. And under this report, we have a new dashboard that we've just introduced that is quite nice to use. In particular, I'm going to draw your attention to RTI and RCI. Okay, RTI, these, for those of you who have taken the Department of Energy DCEP training, Data Center Energy Practitioner training, you'll recognize these. RTI is the ratio of what the racks demand in terms of CFM, divided by the amount of total air supplied by the cooling units, all right, times 100 to make it a percentage. So you always want it to be to the left of this 100 mark, because that means you're supplying more air than you need. If you go back and look again at our summary, the actual numbers are here. 146 is being delivered, 115 is what the racks need. So it's 115 over 146, which becomes a decimal fraction, times 100 gives you that. And essentially what it's saying to you is, you're supplying about 20% more than is really needed. That's a good thing. because generally speaking, in a design like this, you're always going to need to supply more air than is required, because it's not going to get exactly where you want it to go. You don't want it to be over here, because what happens over here on this side is that the racks start to recirculate on themselves because they don't have enough cool air, and you'll get hot spots. Hot spots are indicated by this one, RCI high. If RCI high starts to fall, this is a calculation that is actually the number of hot spots in the room, and also it takes into account their magnitude. You don't want any hot spots. You want it to be in that green range. RCI low is a little less important because this just indicates you're running too cold, and to be honest, it doesn't really hurt IT equipment to run them cold. 64.4 is the low number for the ASHRAE recommended inlet temp. Fahrenheit, 64.4 Fahrenheit. But you can run them colder than that, and it won't hurt them. It's just horrible from an energy point of view. Down here, these numbers are replicated. But this dashboard will give you kind of an overview. This one, a quick overview. This one says, yeah, we're doing pretty good. We have no hot spots, and we're giving it more air than we need for this particular variation. That's an important one. The others are all additional information. So under each one of these, if you want to know which cooling units are on, which the supply, return temps, how much heat they're dissipating, you can look here. It will show you the heat dumped by each one of these units, the heat rejected. So heat removed is listed here. If it's in red, it's a little higher than the nominal capacity of this unit, so we have to look and see if these numbers are going to be realizable. But in general, it's showing you that the units are dumping this amount of heat with this amount of pressure drop across each of those units. This is in inches of water. The units I have set for this happen to be American units, so I'm using inches of water and CFM and Fahrenheit and kilowatts of heat, which is not quite metric, and it is actually metric, it is not English or imperial. This group over here is important as well. This shows you the deviation of the amount of heat being rejected by each of those units from nominal. The nominal heat rejected is 76, but you can see here that this one is pulling a lot more. This one's pulling 42% more than the average. And you want this range to be tight because, or the percentages here to be fairly low. Because, for example, if the one doing all the work here, cooling unit 46, goes down, it's not doing much today. It's only doing 33 kilowatts, so that's okay. I can probably get away with losing that one. But what if I lose this one? This one is 115. This is crack number 9. If I shut that guy down, then the others are going to have to compensate for it. In other words, this is the balance. The balance in the cooling units is represented by this percentage over here. Okay, so you want that to be close to 0 if you can get it there. You want them to be perfectly balanced. Now, that's all the numerical data. Over here are all the 3D files. So the 3D files are shown here. This is a pretty standard. I did turn on animation so you could see them. But the important ones, and these are all 3D images, the most important one is right here. ASHRAE recommended temperature inlet. So what we've done is we've created essentially a go, no-go gauge, if you know what that is. In other words, if it's below 64.4, it's going to be blue. If it's above 80.6 Fahrenheit, in this case, it's going to show red. And what we're showing you here are some of the places where this data center is not meeting the ASHRAE recommended standard. So this is the most important one. This is the go-to, and you can see here that this one's having some trouble. It's having trouble because it's too close to this cooling unit, and the floor is fairly narrow. And so you have high velocity air coming out under that cooling unit, under the floor, and passing right by this section of the rack. If you want to see that more closely, I can show you other plots that illustrate that. But this is a pretty good one to know where the hot spots are right away in your data center. Most people in this business don't like to see any red here. We kid about it. We call it Visine charts. There's an advertisement in the U.S. that's been around for many years. Visine is trying drops for your eye to keep the red out of your eyes, and so we call these Visine plots. Under the allowable range, you'll notice there are no red spots because allowable is a little higher, allows you to go to 90. So this data center is performing okay for allowable, but it's, allowable, but it's having trouble with the recommended standard. We also have a full range. This gives you the full range. Sometimes you like to know, well, how hot does it get up in that corner? I know it's out of range, but how hot does it get? Well, it's getting up to 84 degrees. So what we do is we look at the data set and we spread color out across it. So the minimum temperature is 65 degrees. That's our supplier temp in this case. And our high is 84.4. And you can see 84.4 is right at the top of that rack. Now, chances are you're not going to put a server right up there anyway, so it's probably not that critical, but that's what it's showing. And there are other plots here that will show you that. There are temperature plots like this one. This is a vertical plot showing you temperature in the room at 6 feet of height. You can see it's hot in that region. Again, this is the cold aisle, and you can see the cold aisle is not uniform. It's missing some coolness over in this region again of that data center. And we also have a plot here that shows you that. It is the flow rate on tiles. For a raised floor data center with tiles, this is a nice plot. This one takes a little bit longer to generate or to display. It's already generated because this one is showing you the actual performance. Now, in the CoolSim viewer, this is an ANSYS product. We have keystrokes that shortcuts. I'm going to hit the Y key here on my keyboard, and it puts that right into a top view. And I'm going to hit the letter N, which turns off perspective. And that gives you a really nice view of the performance of those tiles. And we were having trouble over here. You notice this one, near this cooling unit, it's too close, and we have high velocity air coming out from under that floor. And a fairly narrow supply floor, supply plenum. And you can see here that it's down to 600, 650 there. And it goes all the way to 1200. So we've got a factor of 2 in terms of flow rate just across this section of the room alone. And you can see that as well in pathline plots. These are plots that are effectively showing you the airflow by using something called path lines. I'm going to do it from tiles here. I'm going to show you that in this case, the air coming out of these tiles. The other nice thing about this viewer is you can hide objects. So here I'm going to just right mouse click and I'm going to hide that body, and then I'm going to right mouse it again and hide it again, and now I can see through those racks. You can actually see that air bending. So the air is coming under the floor and it's trying to get up out of this tile, but the velocity is so high that it bends. It doesn't go straight up. We don't have enough static pressure right there. Remember, pressure is total of static plus dynamic, and here we've got too much velocity, so it's all dynamic and there's no static, and so I don't have enough air coming straight up on those racks. Common problem, by the way, not unusual, to have a variation in performance of your floor tiles as a function of position, particularly in a room that has perimeter cooling units all blowing to the middle, which is what we have in this case. So that's an interesting plot to look at to show people, and you can manipulate it on your computer with your mouse, and if you want to print this to show someone, you simply hit the P, as in Peter, on your display, and it will create that file. Okay, so that way you can write it out, put it somewhere, share it with your friends, however you like. Pathlines from PDUs and racks is also important. We didn't do them both, supply and return, on the same plot because it gets too confusing. So this is air coming back to the cooling units. You can see this is a naturally convective room. So the air comes up over out of the hot aisle and back to the cooling units. And you can see here that in some cases it's coming between those racks right here, so it's going to mix with the cold aisle. This is the cold aisle right here. And in some cases it's going to recirculate on itself and cause hot spots to occur, probably right over here where we were seeing them earlier. And you can see right now that it's going around and being pulled back into its intake. So this is the intake side, this is the cold side. And you can see that hot air being pulled from a variety of places into that inlet, because the rack, the server, wants air and it doesn't care where it gets it. It's just going to pull whichever is easiest, and you can see it's pulling right up over the top and into the intake. So that's a quick overview of what to look for in the CoolSim interface. And we have both numerical data for every object. We calculate the flow rates. These are the vent tiles, as I was showing you before, in visual. And the rack cooling report shows you the max and min, average, and whether or not it passed or failed, the recommended and allowable output. This information is also printed for you and provided as a PDF attachment to an email you'll get at the end of the simulation. We expand the entire numerical set, and we give you the one plot of the ASHRAE recommended, which is the most important plot if you're trying to design a data center, is that plot. So this is all presented to you as a PDF attachment to an email that you will get at the end of a run. And you can see here there's some failures because in certain cases it's not meeting the requirement. The average is higher than the 80.6. You see right there 82. That's the average, or max in this case. Max temperature is what we key off. And the green represents the coldest room in the rack, and the red represents the hottest room in the rack in the room. Hottest rack in the room. And then vent tiles, crack performance. I mentioned pressure drop, flow rate, supply temperature, return temperature, average return temperature, and then variation. So that's a quick overview of the CoolSim output. I hope you find it useful.